Okay, there we go. Okay, so let's get started. All right, so today is June 13. Let me see where we stopped last time over here. Last page I have here is 94, so this will be 95. All right, so let's look at the problem maybe we were doing last time, and let's change a bit the data. So last time, what is the problem we solved? That's the problem. Okay. So here the idea is again the eigenvalue, eigenvector. This is the same as saying natural frequencies and mode shape problem, okay? So we want to do that with the hand, but also using MATLAB. And see what happens, and see if we can get the same thing. Okay, so let us recall, so let's say here problem, for example. All right, so let's try to solve the same problem that we solved last time, but let's just change a bit the data. We can use the same one. I mean, we can change it as we can see. So we have K1, M1, K2, M2, and K3. Okay, so over here I'm not going to go, this is the class notes that we have been using. So I've been saving over here. So let's see. All right. So when we made it this far over here, page 75, this is the equation of motion, but we can take C1, C2, C3 equal to 0, F1, F2 equal to 0. We can do the, so this is the general form of the equation. So we can write this equation over here. So let's see, the general form of the equation of motion over here. So let's say from page 76. From class notes, the equation of motion is of the form M1, 0, 0, M2, X1, X2, plus K1 plus K2, K2 plus K3, minus K2, minus K2, x1, x2, equal to 0. Okay, so this is the equation of motion. All right, so let's go through the whole process once more, okay? And to find the eigenvalue and eigenvectors. So you assume the data. You want M1 and M2 to be equal to what? Well, last time I think M1 equal M2 equal to M. You want them both equal to M, or you want to change the masses?
We can make them the same again, I guess.
Okay, so M. Then what do we do with K1, K2, K3? Whatever you want, guys. You know, it's just to go through the process once more and.
Just so we can check our work against what we did by hand, why don't we make them equal again?
But isn't that what we did last time?
Oh, I thought we were going to do this a slightly different way so we could compare things, but all right.
Yeah, I mean, we can do, we did that. Okay, let's do this stuff. So is that what we did last time, and then everything was equal to the same, no?
Yeah, I think so.
Is that the problem we did last time in class?
I think so, yes.
Let me double check. So we can do that if you want. I think it's this problem here. I'm just looking at the notes. I put initial condition. Because last time we wrote about like 9 pages for this problem. No, we only had 2 last time.
Oh, okay.
Remember, we only had these ones last time. I mean, I don't mind using the one of last time. I'm just trying to do one more example. Last time we solved this one. Is that the one you said?
No, I was thinking of the one where it had a forcing function.
Forcing function.
One of the masses had a forcing function, the other one didn't.
Oh yeah, I remember which one. So that must be the one right after that then. Oh yeah, it's the one right after that. So I don't have the, okay. Okay, yeah, this one over here. Yeah, so let's do that. Let's take this one, that way we have the solution, and then we can compare. So we have this one over here, where we had M1 equal M2, and all of them are equals to K. Okay, so basically let's just say, recall that problem. So these are all equal to K. Okay, so this is, I'm going to say here C, class notes, pages 91 through 1. You know what, let's do a different one. I'd rather do a different one, because the goal is to do an example.
Okay.
So let's change something in this problem.
M2 equals 2M.
M2 equals 2. That's it, okay? And let's go through the whole process again. And then we can change it.
Sure.
Okay, so if that is the case, over here the equation of motion becomes what?
Would be,
We'll just have to copy over there. We'll have
M0,
0,
0, 2M.
1.
X double dot 1.
And then we have 2K minus K minus K Okay. X1, X2. And here you can just put 1, 0, 2, but it just change. We have this equation, no? All right. So we start going a bit faster over here. Now to find the solution, what do we need to do?
Assume a harmonic solution.
Assume harmonic solution. So let's go a bit faster over here. And it's practice anyway, so 96. So assume harmonic solution, x of j equal capital X of j e. What did we assume last time? I lambda t?
Yep.
Okay? So this equation will become what? If we do it kind of directly, we'll have e I lambda t factor of
Minus m lambda squared
m lambda squared
plus 2k.
plus 2k
And then the next cell would be minus k.
minus k minus k
And minus 2m lambda squared plus 2k.
lambda squared plus 2k. I mean, you see that by repetition is the best way of learning, no? Slowly, we get there. So again, when is this equation satisfied? When x1, x2 equal to 0 with exponential this one equal to 0, no? So that would be the trivial solution. Or when, what do we need to do? The determinant of all this stuff will be equal to 0, no? So what does that mean? Going a little bit faster. That we have minus m lambda squared plus 2k times minus 2m lambda squared plus 2k minus k squared equal to 0. So we need to do here the algebra. So what is that going to give us?
2m squared lambda to the fourth.
2m squared lambda to the fourth. Now let's see if we can combine. So this will give you minus 2nk lambda squared
The other one will give you
minus 4, no?
Yep. So
Would
that'd
be minus 6. Minus 6
km lambda squared. Ought to be.
mk lambda squared then
plus 4k squared
plus
or
4 plus 4k squared minus 1, no? So
Yeah.
plus 3k squared.
Yep.
So every one we can divide this one by 2, no? Or you can leave it this way, or this would be equal to m squared lambda to the fourth minus 3 mk lambda squared. Or no, plus 3 half. Maybe not a good idea. I'll just look at these two. Yeah, let's just read this one. Sorry for that.
Alright.
Okay, so solving. Quadratic equation in lambda square. What do we have? Lambda 1, 2 should equal to what? B squared, no?
No,
No.
just be negative of that. So,
Negative b, so 6
Yep, 6mk.
m k plus minus
Square root of 36m squared k squared.
so 36 m squared k squared minus
24m squared k squared.
times 24 m
That's
squared
convenient.
k squared, no? Yeah.
Yep.
Square root. All this stuff divided by 4
4m squared.
m squared. So if we, oh, this should be a power here to put a square. So what we had here, 6 and k plus minus, this gives us what?
12m
Well.
squared k squared. So you could just make it mk square root of 12. Or actually 2mk square root of 3.
So will be, no, I need to put here 2, no?
Mm-hmm.
What are you doing? Taking the 2 outside the square root?
Yeah.
And then I have the square root of 3. Oh no,
Yeah. There should be an mk on the outside.
yeah, so, okay, 3, yeah, I do that on the next step, okay?
Sure.
I should have put it on this one, you're right. Divided by 4 m squared, so it's not gonna look that pretty. Six and k plus minus 2 square root of 3 and k divided by 4 m squared. So we could cancel almost the m's over here, but all right, so to go a bit faster, let's put some values,
Alright.
since the expression is not that pretty. Hopefully we're not doing any mistake, but that's a good thing. We do mistake, we can check. So, 97. Let us consider what you want to use for m and k.
About 5 kilograms and 400 newtons per meter.
All right. So let's see, that would give us then, let me just rewrite the expression, we have lambda 1 2 squared equals to 6k plus minus 2 square root of 3k divided by 4m. And you see something I never noticed, but this is a good thing. How do we know this is a natural frequency? You see what you have on top, k over m, no?
Mm-hmm.
All right? So I don't know, do you mind doing the calculations? You have a calculator? Well, you know what, guys? Let's just do it together. Let's stop over here for 1 second. And let's say we go now to, we could do a general one, but let's just do for this problem here. Let's say we go to home, computer. We could have done a general problem, you know, with M1, M2, K1, K2, K3. And try different values, but let's just do a very quick MATLAB code and for this specific problem. Okay, what's going on? Oh, computer's off. So what about you start doing the calculations by hand and then we catch up. So if we do this by hand, what do we get? 6 times 400, so it would be 2400 plus, yeah, I don't know. What will you get if you do these calculations?
Let's see.
Give me first the lowest one, so do first with the minus sign.
Okay. Let's see.
Let me go to the computer very quick, see if I can log in now.
Okay, the first one is 50.72 approximately.
Hold on 1 second, let me log in, and then we go. All right, so First one is
50.72, or do you want more?
50.72. What is the next one of the two?
Actually, the 2 was a roundup, so it's a 50.717.
It's fine. I mean, so it's good that it's not going to be exactly the same. And the second one is
One moment. That is 189.28.
189.20. Okay. All right, so let's check those things. All right, so here we go. Maybe I'm going to look here at the class notes, see if I can do this problem more general. That way we can use it later on. What did I have with this one here? Okay. 2 degree of freedom. Yeah, it should not be that bad. Okay. I hate this view, but I think I'm gonna have to live with it. Oh, now it's done. So let's see, this will be example 2 degree of freedom, 8, again, values, again, vector problem. CLC, clear all. All right, so I'm looking at the class notes over here. So you want to go back to the notes, and if you look at the general expression that we use during the derivation of this equation over here, do you remember that was the characteristic equation?
Mm-hmm.
So I'm just going to write this one, A equal M1 and 2, B equal to this, okay, in the code.
All right.
So I can write down then the expression for the 2 roots under this form. All right?
Sure.
So actually here I did a mistake. What should I be used over here? You use minus and this one plus, no?
Yeah.
We want the lowest one. So you see, I need to be careful with that. So let's come over here. Okay. Home computer. Hopefully we get the same thing. So we're going to have to put some data. So we say m equal to what? 5?
Yep.
We're going to have m equal to 5. Then we have m1 equals to m. And 2 equals to m.
Yep.
All right, so then we're going to have A equals M1 times M2, I'm just copying. B equals to M1 times K2 plus K3 plus M2 times K1 plus K2. C equals to K1 plus K2, and we need to put the values for those ones, times K2 plus K3 minus K2 squared. And this problem we had
All the K's.
K equals to 400, no?
Yep. And all the K's are the same.
And then we had K1 equals K, K2 equal K, K3 equal K. All right. So we have lambda 1 equal to minus b minus square root of b square minus 4 times 8 times c. divided by 2 divided by n, no?
Mhm.
Okay? And the other one, we land that over here, should be the plus. So how do we call this problem here? Let me solve it on desktop first, and then I need solve it on the, what can I say here? Okay, I think I'm gonna say it on the desktop first. So what would this be, let's say, again problem, okay?
Sure. It's not typing.
No. Again problem. So we change the order, no? It's fine here. Why change the sign?
Yeah, for some reason it's negative. Huh.
Okay.
Actually, I think,
Oh, I think I know what it is. Because of the original equation,
yeah, we had a minus b.
we had a minus all in front of this stuff.
Yeah.
So I think that's the problem. And we also have minus k squared at the end. So minus k2 squared.
Oh, that should do it.
No, it's good, that should be good now,
Yep,
hopefully.
that should do it.
So there you go, 7.18, 189.28. Obviously, this is not a problem that I want to solve the way I want to solve it, so let's do it here initially. Let me take my cheat sheet a little bit here. I haven't done that in a long time. So, okay. All right, so, yeah. So let me close this. All right, so we needed to do the matrix form. Let me come over here. Let's call the M the matrix. So what do we have over here? M1, 0, 0, M2, no?
Mhm.
And then for K, we had K1 plus K2 minus K2. And the second line will be
Minus k2.
minus K2,
K2.
K2 plus K3. Okay?
Mhm.
So those are the two matrices, okay. So we're still using the eigenvector here, so let's say here, let's do a bit of display. So we could use display, but f print, which let's say this, whatever. And calculations, we do it this way. We probably do some more over here. F print. MATLAB. So let's see, what is that command? Let me look at it. Okay, so the value is, right, so it's eigen. You don't need to put this stuff, but it's to know what is the output. Eigenvectors, comma, eigenvalues is the output. It's too long, it's going to drive me crazy. I have to change the variable. And basically, the only thing you need to put is eigen, so eig, E-I-G, of K bar M, and see what happens. So basically, we put here the semi-comma is going to have this, and then we're going to say we want the eigenvalues first. So let's see. What did I do here? Did I copy it? No. So eigenvalue, here I'm kind of guessing. Do it this way. So it should be our lambda 1. Okay, so see what we get. No error, that's good. Oh. Undefined K1. Okay, it's over here. Oh, because I put it over here. I need to put it after this. F print.
Oh, you forgot to put the F on the end.
F print format, yeah. You can tell I haven't used that for a while. Okay, so lambda 1 equals 50.718, 189.2820 now. And, oops, so this one is 51.718, maybe I'm doing something wrong on the output. Let me see what is the, again, values, how that matrix looks like. Oh, so we need to put 1, 1, 2, 2. So I don't know why you do it that way. Right, so. Okay, so 718, 718, 189.20, 282, and 189.2820, okay? So we got the good one. Now let me do a little bit cheating on here, but I know this is going to create problems. That's why I'm doing it. If we look at the eigenvectors, and let's put the result here. So this is, what is kind of this saying? This was, I guess this column here should be, I don't know if you do it by columns or row, but I'm guessing this should be x1 over here, and this one should be x2. So either they're going to be moving on the same direction, but they are not one-to-one relation, no? And this one will be moving to the left, one will be moving to the right with this type of relation. Okay? So let's see what we get if we do it by hand. And then we can go and compare with this and see what happens. So we have these values. So maybe since we are using the MATLAB 7.718, and this one was 189. Remember the exact values?
Oh, yeah, it was 50.718, if you want to cut it down, and 189.2820.
22.20. Because we're going to be cheating as well, we're going to be doing with MATLAB. So now we have this. So what do we need to do next? We need to go back to this equation here now. For the two cases, we go back to this equation. Now we substitute lambda 1 squared. We solve for x1, x2. Substitute for lambda 2 squared. We solve for x1, x2. So case 1, lambda squared equal to lambda 1 squared. And maybe we can just do the first case with the equation in general. So we'll have minus m lambda squared plus 2k minus k minus k. So we put here like the j, and j is equal to 1, 2. So this is case 1 and case 2 at the same time. That way we can save some time. So it would be minus 2 m lambda j squared plus 2k x1 x2 equal to 0. So let's just solve for 1 over here. So from here, what are we going to get? Minus m lambda j squared plus 2k x1 minus k x2 Okay, let's do both of them if you want, equal to 0. And the equation we're gonna get is minus k x1 plus minus 2m lambda j squared plus 2k x2. That must be equal to 0, no?
Yep.
So let's say from just one of them, because it should give you the same result. So let's use the first one. What are we gonna get? Minus m lambda squared j plus 2k x1 equal k x2. So that means that, I don't know, you can just put the value, so, or x2 over x1 will be equal to minus m lambda j squared plus 2k
Over k.
over k. Okay, so help me over here a little bit, see, because I won't, Anna should be able to see the paper, so computer. So let's say we'll have over here, I mean, maybe we should do it differently. I mean, it doesn't matter, we can go back and check. So x2, let's say here over x1, for let's say, this is going to become complicated. Lambda 1, for lambda 1, okay, will be equal to what? Minus m times lambda 1 squared.
No, in the code we have it as just lambda 1.
It's just lambda 1 because it's already squared. Yeah. Lambda 1 plus 2 times k divided by k. And this one will be lambda 2 minus m lambda 2 divided by k, no? Do you see something wrong here?
Looks alright to me.
All right. Okay, so we do that, let's see what we can do with those results. So 1.366, negative 0.366. Okay, or here we're gonna have x2, x1 for the first mode was equal to what? 1.366?
Yes.
And x2 over x1 for the second mode was equal to nearly 0.366.
Yes.
So do we do this stuff here? Okay, so I know I may have changed the notation. Okay. So, and eigenvector lambda 1 square and lambda 2 square. I mean, I'm giving you the answer here, could be what? So let's say for the first one, what do you want to select?
Would be 1 and then 1.366.
So we select x1 equal to 1, x2 is going to be equal to 1.366. And then for the second one, let's do the same criteria then, no?
Sure.
So if we select then 1,
Yep, and then negative 0.366.
0.366. Okay, so let's try, I'm gonna have to do a little bit of cheating here because I don't know exactly how MATLAB is working. So here basically what I want to look at is now at the, from MATLAB at the eigenvectors.
Mm-hmm.
Let me erase this. I don't like this configuration. So
Here. I'm going to try multiplying the first one by,
yeah, but I think what I'm trying to say is that do they go by line or column? I think they go by column, no?
I think so, but.
Yeah, if you divide, so let's see, if you divide the lower one by 0.2056
Yeah, it goes by columns. It's the first eigenvector is the first column, second eigenvector
is the first column, no? That's what I thought. So if you want from this one, okay, so I'm just gonna put it here on the dot com, or I'm gonna lose, you don't have to give me those values. I put it back again, or let me write it down here. So the first value should be negative 0.2056, negative 0.2808, and the other one is going to be negative 0.3972, 0.1454. Okay. So basically what I'm going to write down over here is that our MATLAB is what? It's giving you negative 0.2056, negative 0.2080, and x2 negative 0.3972, 0.1454. So now comes the question, I think you already found the answer, but why are they different? Are they really different?
Not really. It's only the proportion between the numbers that matters, not what the numbers are.
Okay, so what does that mean? Do you remember we had a little discussion about what is the physical meaning really of the eigenvector?
Yeah, you said it's, if you think of it as a vector, it's basically the direction, not the magnitude.
Correct, so a vector has an infinity number of direction vectors, no? Okay, and the magnitude doesn't matter. So what happens is that the value of the eigenvector is going to depend with what you compare it. What is the reference value? For example, in this problem here, we selected x2 to be 1, or x1 to be 1, no?
Mm-hmm.
But we can select x1 to be any number, and then x2 will change. Does that mean that then that those eigenvalues we found are wrong?
Nope.
No, because our selection was first to select x1 equal to 1, correct?
Mhm.
So if we take these values over here, what do we need to do to make this one 1?
Divided by negative 0.2056.
Correct, so let me just write over here is that eigenvectors only give the direction. The direction, but in this case, is what I call the mode shape. Of the deformation. And not the magnitude. Okay? So what does that mean? Is that then they can be multiplied by any constant. Yeah?
Mm-hmm.
So basically for the first mode, what can we do? So let's say over here, so we do the MATLAB X1, we have negative 0.2056, negative 0.2808, and we multiply that one by what?
1 over negative 0.2056.
Yeah, so 1 over negative 0.2056. What do we get? Yeah, I can do it by
1 to the top, definitely.
1, and hopefully at the bottom we get exactly the other one. So home, computer. So let's see, what do we do over here? There's probably a more elegant way to do this. So, all right, so let's see. How do we call this one on top? Oh, we didn't do the eigenvector on top. Okay, it doesn't matter, we have them. So, oh wait, shouldn't this, oh no, x2, x1, shouldn't this be the hand calculations?
Well, that's the ratio between the values.
Yeah, but by hand, no?
Oh, yeah, yeah.
And now here we have, like, let's say, egg, vect 1 was equal to what? Eigen, what do you call this one? Eigenvectors.
Would be colon,
Take
comma
it to the
1.
first column, no? Is that this way to do it, or
I think so.
we'll find out? Very quick. Eigenvectors 2 should be this one. So let's run this very quick, see if that's one. We get, yeah, nearly these ones, no?
Mm-hmm.
So we want to rescale this. Okay, let's do it here right away if you want. So we want to divide this one by, so the first one we're going to divide this one by the negative of,
0.2056.
well, maybe I can do it this way, no?
Actually, it's 2 complicated.
1, 1, no?
Yeah, that should work.
That should work, no? And the second one will be the second column. We'll be dividing that one by what?
Eigenvectors 1, 2.
1, 2, okay, I trust you, you'll find out quick anyway. The negative as well? We'll find out. It's gonna be,
Yeah, I think
you know.
so.
So the first one will give us, oh, so what do we have a negative value?
Oh, we shouldn't have put negatives in there since we
It will be 1, 1.366, the same thing we have on the other one, and 1.366, no?
Yep.
So we should not have the negative values over here. But basically, we should get the same values that we got over here. Over here. Oops, so. So the eigenvalues coincide. What do we have over here for x2 over x1? 1.366, no?
And the next one, negative.
And negative 0.366, which is the same thing as this one and this one.
Mhm.
Okay? So you see that you need to be careful here, because it's not that you run the eigenvector and you don't get the same answer as your hand calculations, that you have done something wrong. You need to realize that the eigenvectors, they just give you the direction or the shape of the deformation, and that, that is what really matters. Okay? And you can just multiply or divide by a constant. So this one and the second one, so that was giving us 1, 1.366. And if we do the same thing for the other one, we had x2 equal to negative 0.3972, 0.1454, or maybe let me remove here no, but here we needed to multiply by the negative, no?
Yeah.
Okay. Oh yeah, because already taking the negative when you do the other way. And now we want to multiply this one by basically 1 by the negative of 0.3972. And by doing this, we get the same as the other one, which is 1, negative 0.366. Is that correct?
Mm-hmm.
With my other page. Yeah. Okay, so something that I haven't done in this problem, but that generally I do in my solutions, is that, so if you want, this would be the end, but something that I like to do, for example, when I have this x2 over x1 for the first mode shape equal to 1.366, I know it's not exactly that in this case, but I like to do some type of representation, okay, some type of figure. So basically, what does that mean? Let's say it would be M1, this would be M2. So what do we see over here is that when M1, when x2 is moving 1, no?
Mm-hmm.
How much will be x2 moving?
1.366.
1.366. Okay? So it just shows they're moving on the same direction, but different values. And for the second one, which is here, which is x2 over x1 for the second mode is equal to negative 0.366. So we do something similar. What are we going to have? If x1 is moving 1,
Mm-hmm.
how much is this one going to move?
Negative 0.366.
Negative 0.366. So I like to show that they will be moving on the opposite direction, no?
Mm-hmm.
All right? And that will be the ratio of the displacement. You cannot know how much it is on the real case. Those will depend on what?
Initial conditions?
On the initial conditions. The value of the amplitude if you want, or those things will depend on the initial conditions. But the ratio will always be between 1 and 1.366 if this system over here, let's see what is my initial page. So if initially this system over here is rotating at the frequency omega 1 squared, the both will be moving, let's say, to the right or to the left. When this one moves 1, this one will be moving
1.366.
1.366. Then, when they vibrate at the certain natural frequency, lambda 2 squared, when this one moves 1 to the right, this one will be moved 0.366 to the left, no?
Yep.
Okay? Or vice versa. When this one will move into the left 1, this one will be moving to the right 0.368. Okay? So that's the physical minimum. What's important is that you are able to see from the equation the physical minimum. Because otherwise there is no point to write fancy equations, no? All right, so 95, 96, 30, 38, okay, 99. And that's it. So this will give you this. This is pretty quick to do, but again, we only use two modes. If it was more, it would be a bit more complicated. All right, so we're going to do this. That will be it for now. I'm going to do this. Okay, I already said, but repetition is many times the best thing. So what's the conclusion about the eigenvalues, eigenvectors? The eigenvalues will give you the natural frequencies. The eigenvectors, you might get different results for the eigenvectors. But they should all give you basically what is the general shape of the formation, no? If one is moving to that direction, the other one will be moving in a ratio on the other direction, or the same direction. So that's the important thing. We still have about 20 minutes, so we can do whatever you want. You were talking that you wanted to look at one of the homework problems?
Yeah. Do you have a copy of the homework or?
No, I don't have it.
Here,
Wait, I might have one. Is it homework 3?
I think so.
Yeah, I think I have it here. Yeah, I think it's the one I just put on top.
You can borrow this one too if you want it.
I think I have it here. It's just the page that I put on top. But organizing my notes. So let's see if it is the one I have. So this is from homework 3. Problem 2. So it looks like I give here a figure. About having the wind turbine, a blade, some type of mass over here, and a distance E over here, no? Is that what it is? And then a distance R over here. I don't know if we need the H. Yeah, I think we need the H. And I say design the diameter and thickness of the base. So basically what I need to design is here. Thickness and diameter, no? And for that, what did I give you over here? So a damping of 2%. Then an omega, I don't know if I call it capital omega, of 16 RPM. And then I say that the maximum of the base for a maximum of 5 centimeters of the vertical pole. So then what I'm asking is a vertical, so a maximum deformation of this. So I don't know if it will be on which direction it will be, it doesn't matter, let's say it will be on that direction. Let's say delta here of 5 centimeters? Okay, so I don't know if you have enough data as you mentioned to me. So, I don't know, we have to look at the notes over here. Again, I made up the problem, so, you know, I don't know if it's an exact solution or not. But this would be,
If not, we can just do it symbolically, I guess.
yeah, you know, just do a design. So basically, I think the equations we had over here is that, so I'm just gonna look at, so basically, okay, that doesn't mean that you need to do the problem this way, okay? I'm just thinking with you aloud. So first I will say here, considering just bending, no shear, okay? Maybe it would be good on the second part to go and check after the thickness if this is going to be resistant enough for shear, no?
Mhm.
Yeah? But let's just say my initial design will be not for bending, not for shear.
Okay.
So if we do it that way, what is the equation we are concerned when I have the MC over I, no?
Yep.
Okay? So, okay. So from this equation, just gonna do it this, you know, thinking aloud.
Actually,
We know C should be equal to what? The diameter over 2, no?
mhm.
On the outside. And the I don't remember, was pi over what? 32, 64, I don't
It's
know.
pi over 4. Oh, well, actually, oh, wait, if you're going to do the, in terms of the diameter, then yeah, it's pi over 64.
64?
Yeah, pi over 64, d to the fourth, d to the fourth, minus 2.
So outside to the fourth minus to the inside to the fourth, okay? Something like that, okay? I don't care about those values that much. I'm just going through the procedure. So and the next thing we can do is, so we know C, we know, C and I. And I think the next thing I say is that you can know sigma, no? Did I say to use cast iron or cast steel?
Yeah, cast iron.
Cast iron. So you can find this value from any solid textbook, no?
Mhm.
I don't know what would be the value, but this should be given,
Mhm.
all right? So now, what should be M? So this should be from some type of, from material table. And what is M? M, when we derived this stuff, was equal to some type of,
Some force times r probably.
was M capital omega square, no? Times E.
Something like that.
That was the magnitude.
I think so.
Times, so that was the value of the force. Okay, again, I'm not going through the details, I'm just giving you ideas, no?
Mhm.
Force times, and then here we have the distance r to create the moment, no? For the r.
Mhm.
But this is a different r, so r over here. Okay, so this is 1. Then we know capital omega, so we know capital omega. We don't know M, we don't know E. And we don't know R. Okay, I don't know how to do it yet, okay? But let's keep going through those things. Next thing we know is that the deformation, this one. So we can assume, I think we kind of discussed this a little bit already. If this is a cantilever beam, okay, this is a cantilever beam over here. What is that telling us?
That the deflection is proportional to the load.
So force, yeah. Then we say it was equal to this.
Looks good.
All right, and so if we compare, I think we already did this, so we compare this equation here to FLQ over 3EI. So you can find the I from the material, the E from the material, no?
Mm-hmm.
Okay, the I from this, the same thing. The force is this one. The L here will be really H, no? That we don't know. I'm going to compare that equation and let's say force equal K delta. What would be K?
K would be 3EI over L cubed.
Yeah. So we compare these two. We get K equal 3EI over really will be H cubed, no?
Yeah.
So what will you have? Let's see, let me think about it. I think I'm going to have to give you H. Because this, we still have the unknown of the diameter, no?
Mm-hmm.
It will be known. And if we know K and omega, you can find M. Yeah, I need to give you two more things. I think I need to give you a bit more. So, I mean, you want me to give you some more data, or you just want to leave it that way and you do a critical? I mean, you see what I'm doing here? I'm trying to put everything, no?
Yeah.
Yeah, but it would not be true to say the omega. All right, you give me the values. So, and then I need to remember to put it online. So which one you want to use for H and for E? And I think that should make you do it. So what do you use for H?
How about,
They're pretty tall, those
yeah,
things.
I was thinking 100 meters?
No, 100 meters is too high.
Okay. I'm used to American.
I will say, but they are probably about 20 meters.
That's fine.
I mean, 20 meters will be about 60 feet.
Okay.
60 feet is a lot.
Yeah.
And E, the unbalance, what do you want to do? Like maybe 5 feet, 10 feet?
Okay.
So let's say about what, 3 meters?
Yeah.
Okay. So let me just add this stuff right away for Erin, I guess. So, computer. But if you use it, you know, guys, I'm looking a lot more about your criteria about the design, no?
Yeah, yeah.
I'm not that concerned about values. I know students are concerned about values and results, but I don't understand why, okay? I get this. To me, it's a lot more, I mean, what I'm trying to motivate here is not your advanced skills, it's to get your engineering skills, no? Your critical thinking and design skills. And if we're not many in class, we can do it. We were a lot, no way. I will never do that. So homework 3, 8. So what I say here, in problem 2, use H equal to 20 meters and letter E equals to 3 meters. You want to submit it online? That's what we have been doing, or you want to submit on paper? I think we have been doing online, no?
Yeah, we've been doing online, and since it's due at midnight, you probably don't want us finding your house and knocking on your door.
I might not be there, so no. File uploads, what did I say here, restrict to PDF? Yeah, I don't, you know, if you want to put your code and those things, is fine, but unless I require, generally I'm not going to run it, I can just look at it, okay?
Alright.
So I don't know, I mean, maybe I might be missing something, but by just looking at this, it will look like, to me, I think I can solve from this. Okay, maybe I'm missing something, so I'm not working out. So, to me, if I have to do the design, this will be my first step. So you can find a value for the diameter, okay? Then you can find if that diameter is reasonable for the shear, all right? So on the shear, what are you gonna check? Are you really gonna check the shear value? Or maybe you want to calculate what? I mean, the same thing, you know, people when they think about shear, that's a problem that people do many times when they do design, is that they look at the material and they say, oh yeah, this shear, this value we get is a lot under the maximum shear value, okay? But that's not that important to me. The important thing is the angle of twist. It might be under, but what happens if that stops twist a lot? Everything is going to change, no?
Mhm.
So maybe once you find this and you find the thickness, try to find what will be the angle of twist for that cross section,
Okay.
even though if it's safe. So as you remember, I think the shear stress is TC divided by J.
It's TL over, oh wait, shear stress or the angle of twist?
No, the shear stress is TC over J.
Yeah.
And the angle of twist will be TC over GJ, or T over GJ.
TL over JG, yeah.
Yeah, J, GJ, okay? Now you're gonna find what it be. And if you find it reasonable, it's good, but if you don't find it reasonable, maybe, yeah, you're gonna reducing the bending, but you wanna be sure of this one,
Mm-hmm.
okay? Because it doesn't have to be 5, if it's lower, better, no?
Yeah.
Okay, that's the idea, because, and here the interesting thing to me, all you're gonna say is, yeah, there is vibrations, but it's also solid mechanics,
Mm-hmm.
okay?
It's primarily solids.
Which is, I think, is interesting many times is that we look at the courses on a vertical way, and sometimes it's better to look at it in a horizontal way, no? How can we combine our knowledge about the different stuff? But again, like I told you, I think like on the one, I'm not looking for one answer or everybody doing it the same way. Trying to see what is your approach to solve the problem. My idea, my initial thoughts would be these ones.
Okay.
If you find something completely different, don't feel bad about giving it to me, okay? I'd rather see something completely different than something that is following this and nothing else, okay?
Mhm.
So I don't mind even if you find it's too extravagant, I don't care. I want to stimulate your critical thinking.
Alright.
So is that enough that I can give you for this problem, or?
I'm happy.
Happy, okay, so if you're happy, that makes me happy then. All right, guys, and I've been trying to catch up the class notes, I put them online, but the videos, it just takes forever. To upload those videos in YouTube, to make the PDF, to transform the video file into YouTube, it takes an hour
Jeez.
or 40 minutes, between 40 and 50 minutes. So, and sometimes it doesn't do it, so I need to leave the office, come back to the office. But I think I was able to upload today up to at least last Thursday. And I think I was doing now, hopefully it didn't crash, I was doing yesterday's class, okay? So I try to keep up, okay? So that'll be it for today. So remind me tomorrow that to prepare your last exam for the end of this week, okay?
Okay.
So that you have plenty of time to do it.
Alright.
And again, I would try to give you problems about, like maybe some direct applications, like the problem I gave you to combine the response of two ones, and then some that will be more about design.
Okay.